Hello, and welcome to the 2024 Commodore 64 Repair-a-thon on yet another retro channel. Today we are going to attempt to work on machines 9 and 10. I'm hoping I can get through both of them. I'm hoping that at least one of them will be a simple repair, but you've seen what's come before. You know that these things never go to plan. So do I really need to tell you that that's not how this went? Machine number 9 is another marathon, so we don't get to machine number 10. I'm coming to the conclusion that I kind of got boned on this lot of C64s. I bought it from a gentleman who was selling his recently deceased father's collection, and what I think I actually got was 10 machines that he hadn't been able to repair, which is why these are so complex. He probably took care of all the low-hanging fruit, machines that just had bad PLAs or, single bad chips or whatnot. I, on the other hand, got the ones that were beyond his either ability or required more specialized equipment or required spare parts that he didn't have. So that, I think, is why these machines are more complex and giving me more trouble than average. But I don't mind doing them because, one, it makes for interesting content for you guys to watch. Two, it makes it interesting for me to do. And three, I learn a lot from this. Hopefully you can learn along with me. But for instance, in this video, I'm going to learn a lot more about how the cassette port operates. That's something that I wouldn't run across if I hadn't run into a problem with the cassette port. It also gives me a chance to hone my skills and get better. I hope that you're noticing that as I'm doing these, each video, I don't make the same mistakes that I made in the previous ones, and perhaps my technique gets a little better each time. So that being said, settle in, get yourself a snack, something to drink, and come with me on the journey. So what I am going to try to do to see if I can make this go a little bit better is be a little bit more methodical in my process. You guys know I'm kind of all over the place when I do these repairs, jumping from thing to thing. I am going to try with these machines to go through the process a little more systematically, a little more process-minded. So hopefully we can get through them quicker. And with that said, let's get on with it. This is machine 9. It's in pretty good shape physically. Dirty as usual, needs a cleanup. Keyboard feels pretty normal. We'll take a look at the bottom here. We have a note that says power light and black screen, so we expect the power light to come on and there to be no video output. We have 3 of the 4 feet. We have all 3 screws. So let's hook up to video and power. And I do have the power supply switched on. And we will see what we get. As reported, the power light is on. And are we getting any video output? I'm not seeing anything. So we may have another VIC issue or timing chip if it's a later revision board. So, time to open her up and see. And we do again have a later revision 250425 board. So, keyboard off. And what do we have? Okay. We have no contact between the VIC-II and the heatsink that's supposed to be, actually any of these chips. Well, the PLA seems to be touching. The SID's not, CPU's not, the 3 ROMs aren't. So that's not acting as much of a heatsink for anything. And there goes the shield. We do still have the bottom shield, so if we need to do any work, we'll have to remove that. We have fully socketed RAM. We have sockets under all the main MOS ICs. I'm seeing date codes, 35th week of 84, 23rd week of 84, 51st week of 82 on the 6581 SID, 37th week of 82 on the CPU, so there has been some replacement in here. Our CIAs are both 25th week of 84, 29th week of 84, 16th week of 83 on the kernel, and 34th week of 84 on the character ROM. We have socketed MOS logic multiplexers. I'm not seeing any other MOS logic chips. So we have MT RAM. That could be an issue. There's 4 of those. That's Mitsubishi, 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 Mitsubishi. So we have MT and Mitsubishi RAM, MOS logic, multiplexers, and the rest is standard logic. So the first thing I'm going to do is check continuity on the fuse. Okay, so I tested the fuse in the fuse holder and it was showing open, so took it out, and just to be sure, there it is, wide open. We need a new fuse. I'll grab that real quick. Okay, a new 1.5 amp 250 volt fuse, and let's see, because that controls the 9 volts, which is then fed through the bridge rectifier and the regulators to provide the 5 and 12 volts to both the VIC-II and the SID chip. So since we've replaced the fuse, let's see if we get any video out. Okay, we are now getting video out. We have a black screen. So that's going to imply that both the clock generator chip and the VIC-II are probably working. We're not going to make that assumption this time like we did the last time, so we're going to check signals before we're sure that, of that. But for now, let's go back to checking our power system. So our regulators, this should be the 5 volt regulator. We should be getting, we're at 5.12 volts. That's absolutely fine. And 12.07 volts for the 12 volt regulator. That's absolutely fine. So we're getting the proper voltages out of the regulators. Let's check the 5 volts. Kind of backwards again. Check the 5 volt rail coming through the board. This is coming from the power supply, and it is being dragged down to 4.43 volts. So we likely have a shorted chip somewhere. And then AC voltage, and we check again on the user port. 10.05 volts coming through from the power supply for AC, and that is just fine. So what we are sure of at the moment is that we have the proper voltages going to both the VIC and the SID, and we have a proper AC voltage coming through the system. So the next thing that we need to check are our reset and our clock signals. So we're going to switch over to the oscilloscope and check first the reset signal on the 6510, which is pin 40. Now this should stay low for a moment and then go high. And it does. So we have a good reset circuit. The next thing we need to look at is our clock. Now this, we'll need to set up some measurement, frequency measurement, and let's see what we're getting on the phi-0 in clock. That is on pin 1 of the CPU. We need to adjust our time base, and we are in fact getting a good 1.02 megahertz on the CPU clock. So our reset and our clock are both good. The next thing I'm going to check is the PLA, and I'm going to check that this time rather than by using the ZIF board. I am going to walk through the PLA and see what some of the signals look like, see if we have any signals that are being held high or held low or floating or anything that they shouldn't be. So we will start, let's see, let's start on the ROMs. Those are pins 15, 16, and 17. Pin 15, oh, sorry, PLA, not SID. Pin 15. Pin 15 is character ROM, and that's constantly low. Now that does actually make a bit of sense because we're not getting anything on the video. So let's look at kernel. Kernel's constantly low. That should definitely have some activity on it. And here is basic. And basic is constantly low. So we have indications that the PLA is bad. But let's look at I/O. That would activate the CIAs. So that's going to be pin 12. And that's floating. Okay. We have an indication that there might be a problem with the PLA. Normally, I might have jumped to testing that in the ZIF board. This time I verified that there is a reason to test it. So what I'm going to do is I am going to pull the PLA. Since it's in a socket, it's pretty easy to do. Pull out our PLA, and we'll get the ZIF board. Make sure the ZIF board is still working, and it is. So we will now pop the PLA out of the ZIF board and put our suspect PLA in. And what do we get? We get black screen. So I'm not going to just automatically assume I'm going to reseat here because there could be a problem with connectivity in these ZIF sockets. They're not perfect. They're good, but they're not perfect. So let's try that. And still black screen. So this time the PLA is a problem. So we get one of our replacement PLAs, verify in the ZIF board that it is working before we put it in the suspect machine. Okay, that's not great. Okay, just a bad connection. Like I said, those ZIF sockets are not perfect. So that PLA does work. Let's go ahead before we get ahead of ourselves and mark this PLA as bad. And this one, the one that I've just tested, is good. And let's seat this replacement PLA in our 64. Yeah, it felt like it went in good. I don't see any obviously bent pins. So, what happens now when we boot this? Okay, we're still black screen, but we know we've got a good PLA in now. And let me just check and make sure I didn't bend any pins. Nope, everything went in fine. And let's just to play it safe. Deoxit that socket. It is a single wipe kind of crappy socket. So let's put that back in again. Okay, we're still black screen. So let's actually check some of those signals now. The ones that we saw that were bad. First, I'm actually going to check the DC voltage at the user port again. It's actually worse now. Well, that could indicate, I suppose, that one of the chips that wasn't being selected has a problem, and now that it's being selected, it's got a worse short. So, let's check those signals again that we checked before on the scope. Now let's look at kernel first. Plenty of activity on kernel. Basic should only have activity at the very beginning unless we were to do something with it. So let's see what happens when we start up. And there's activity on basic. And character. There's activity on the character ROM. And no activity on I/O, but it's no longer being held down at around a volt. It's up where it should be. So the next thing we're going to look at is we're going to go ahead and pull the SID, because that could be bad and that could be causing issues, and we don't need it for testing purposes. So I'm going to pull it out of here. And now see if we get anything. Still black screen. Okay. So the next thing I'm going to do is I'm going to pull all the chips that don't need to be in here for dead test. So the 3 ROMs, the 2 CIAs, the SID do not need to be in the board. So let's go ahead and pull these. I'm going to do it one at a time, checking the voltage each time at the user port to see if we get any change. So with U1 pulled, do we get any change to the voltage at the user port? No, it's still down around 4 volts. So that likely isn't our shorted chip. Next CIA, U2. Is that our shorted chip? Nope, still around 4 volts. Basic ROM. Are you our shorted chip? Well, it's actually a little bit better, but I don't think that's enough to show that that's the shorted one. Kernel. Kernels often short out, I find. So, were you the shorted chip? No, that's significantly better, so there's a good chance there was a short there. Okay. And character. And without character, a slight improvement, but not much. Okay, now for shorted chips, our next most likely candidate is going to be RAM. Now let's actually leave this on for a bit and see if we're getting any hot RAM. I don't think. Well, possibly some of the MT RAM is warmer than it should be. But our next step is actually to try dead test. Now that we have only the chips in that are required for dead test to operate, we are in dead test mode. And let's see if we get anything. We get a single flash. So let's try rebooting and see if we get the same thing again. We do indeed still get a single flash. So a single flash is U12, 9, 10, 11, 12. And if that was U12, that's going to be this guy right here. Now, since we've already replaced the PLA, it's more likely that the flashing from the dead test is accurate. We all know that it's not a 100% reliable test, but I'm willing to take a shot at this point and see if this RAM chip is an issue. I think I saw, Jesus. Here we go again. All of these RAM chips are in just simply, this person, whoever did this to these machines, I want them found and shot. This is not good. So before we go any further with diagnostics, I'm actually going to go ahead and pull all these little pins and replace them with proper sockets. These things are they're metal, so if they happen to touch each other, that's your short. It was a really bad idea to put them in there. There's nothing in between them to keep them from shorting out against each other. That's just not acceptable. So we're going to do a zip cut and a better starting point. Okay, I have replaced all those just pins that, well, as I said, that previous technician had used simply pins, not sockets, to fit the RAM. And since there was no plastic casing, there was nothing preventing any of these from shorting out against any of the other ones. So I don't know if that was what was causing the short or not, but I replaced those all with proper sockets. And I did find some poor work in the soldering and desoldering. I found 2 torn traces that I had to bodge around on the back. I added 2 bodge wires back here. I don't know if you can see those, but there's one here and one over here to complete the circuits. And then I toned out all the sockets and made sure all the connections were going through where they're supposed to, and there are no bridges, no shorts. So it is time to give this another test. We're still going to be using dead test. Let's get that wrong. There we go. So we're still on dead test, and we're going to see if we get anything. Nothing at all. No flashes and no dead test. Now I left the Mitsubishi RAM in, and I replaced the MT with known good RAM from my stock. So I'm relatively confident with that. Why are we still not getting dead test? Oh, gray screen, that's new. Let's make sure our dead test cartridge is in there, okay. Gray screen. Interesting. Now it's black screen again. Okay, I haven't been able to leave it alone, so I did some signal checking, and again, here's our clock. Oh, wait, turn it on. There's our clock, still good at 1.02 megahertz. Pin 2 on the CPU is the ready signal is active high, and it's high. Pin 3 is IRQ, and that's active low, so we're not in IRQ interrupt. Pin 4, however, is the non-maskable interrupt, NMI. Now that, with no CIAs in place, because the NMI does appear on the CIA in U2, with no CIAs in place to trigger it, the only other things that would trigger it would be the cartridge port, which nothing's in the cartridge port right now. I've pulled the diagnostic cartridge dead test out. The only other thing that triggers that is the combination of the 556 timer and the 74LS06 over here. Now, the 74LS06 is a quad NOT gate, so the input for that is pin 5, 1, 2, 3, 4, 5, and the output is pin 6. So what we should be seeing is a low on 5, which we are, which should then be negated to a high on 6, and we're not getting that. So VCC, it's getting a good 5 volts. Ground is ground. Input 1, which I'm not sure where that comes from, but input 1 is getting about a 1 volt signal, and it's being negated to 0. Input 2 looks like a clock, and there's output 2, so that's working. Input 3, not inverting the 0. So I think we have a bad 74 LS06. So I will need to desolder that, socket it, and replace it. So the 7406 does fail in the TL866 programmer tester. So let's get a friendly little socket in there. Okay, and one 74 LS06. Pin 5 is low, pin 6 is now high, and our non-maskable interrupt on the CPU is also high. So now let's see what happens with that test. If you enjoy this type of content and want to see it keep coming, there are a few free and easy things you can do to help. Like the video by clicking that little thumbs up button. Likes encourage YouTube to offer this video to more potential viewers like yourself. That helps the channel reach more people. Drop me a note in the comments section below. Comments show YouTube that viewers like you care enough about this type of content to engage with it on a more personal level. Subscribe to the channel and click on the little bell icon so that you'll be notified when new content becomes available. Finally, share a link to this video with your friends or in your social media groups. That again helps expand the reach of the channel. If you're feeling generous and decide you want to support the channel financially, there are a few ways you can do that too. You can become a member of yet another retro channel by clicking on the join button below. There are also Patreon and Ko-Fi links in the description below the video. I do appreciate all your support in whatever form it takes. Thank you. And now back to the video. And here we go. Okay, no flashing. But still no dead test. Okay. Go back to checking signals. So there's the clock, 1.02 megahertz, we're good. And still, yep, we're still good on reset. Ready. Active high is good. IRQ, no interrupt, good. NMI is now high, that's good. AEC looks like it should. VCC, that's high, that's 5 volts, that's good. And then we start with the address bus. So address 7, or address 0, pin 7, looks good. 6 looks good. Or pin 8, address 1 looks good. Here's address 2, that looks good. Address 3 looks good. 4 looks good. 5, 6, 7, 8. Interesting. Not fond of that. So 8 is, address line 8 is a question. Address line 9. Yeah, nothing there. Address line 10, that looks okay. 11 looks okay. 12, not so good. 13, 14, oh, sorry, that's ground. 14, yeah. Activity and then nothing on 14. 15, normal activity and then nothing. Okay. Well, those address lines do connect to the multiplexers, and the multiplexers are MOS logic. So the next very simple test we can make, since these are already socketed, is to go ahead and pull them and test them in the Mini Pro. Okay, the U13 multiplexer tests bad. Go ahead and check U14, or sorry, U25. Oops. That one looks like it's had a leg soldered back onto it, so it's had issues in the past. And how does it test? It also fails. So let's try a pair of brand new 257s. Okay, with a new set of 257s. So let's look at the address lines again. Address 0 still looks fine. 1, 2, 3, 4, 5, 6, 7, 8. Nope. 8's good for a moment and then goes flat. 9. Good for a moment and then goes flat. 10 looks good. 11, 12, 8, 9, 12. 13. 14. 15 is never good. So make sure the multiplexers I put in were both good. Yes, they both test good in the Mini Pro. So there is something else going on. All right, I've hesitated to go down this route because apart from putting it in the ZIF board, I don't know any other way to test it, and I've been trying to avoid doing that with this, but we could have problems with either the CPU or the VIC-II. So let's pull them both and test them in the ZIF board. Check the VIC-II first. Working-ish. That's not great. Let's make sure we're not poorly seated here. Huh. Oh, we're missing a pin. Part of a pin anyway. This may be reparable. For now, we're going to swap it out. Just so you can see that. Pin number 21 is broken off. And pin number 20 has been soldered back on once already. So again, last technician to work on this board. Not great. So we'll try to fix that later. In the meantime, we will grab another working 6567R8. So this may not be a total loss. And this is the one that came out of this ZIF board. Make sure we're still working. Interesting. Okay, since the ZIF board isn't working, here's another board. And let's make sure that it's working. And it is. So let's pull its VIC. Verify that this VIC we're going to use is going to work. And it is. So this is a good VIC. Let's check the CPU. There's the CPU in, and try it. Looks like we have a bad CPU. So I did not bend any pins. Well, CPU is partially working. Oh, black screen again. So I'm going to take a punt that we have a bad CPU. Make sure this board still works. Put the original CPU back. And it does. So, pretty good shot. We get a bad CPU as well. Not great. So, replacement VIC-II. And replacement CPU. And let's see what we get now. Now remember, we do have dead test in here. So we'll get the scope in case we need to look at those address lines again. Let's go ahead and put it on address line 8, which is the first one that was bad, is pin 15. Yeah, I can't at the moment show you both the scope and the output at the same time, so I'll just have to tell you what's going on with the scope. Address line 8 still goes high. As does 9. It looks like something, I don't know how well you'll be able to see that, but it looks like it's trying to work and something is holding it high. So, what else is on those address lines? Okay, so I think I actually have this figured out. Let me cover a couple of pieces of housekeeping first. The Moss branded multiplexer logic chips. I said those were bad. Actually, it turns out I tested them incorrectly in the Mini Pro, so these are actually good, but I am not going to return them to the board because, again, they are Moss logic chips and they are likely to fail at some point, so they are leaving. And I will leave the 257s that I replaced them with in the board. The 7406 is definitely bad, so replacing that was a good idea. I'm also not going to return the MT RAM, the 4 MT RAM chips, to the board. I don't care if they're good or not. They're likely to fail at some point, so they're not going back in. And of course, we did have the original bad PLA. Now, the other thing it was that the ZIF board wasn't working when last we looked at it. And just to show you, I have solved that little issue. It was actually a pretty simple problem. I simply had the PLA not seated well in the ZIF socket. So now that it is reseated, the ZIF board is working fine again, and we'll need that in a moment. So, back to the board that we're working on. As you can see, I have the dead test in, and we are still getting nothing but a black screen. So I was testing address lines off the CPU. Now, I have since verified that the CPU is working absolutely fine in the ZIF machine once I repaired it. And I also took the time to solder new legs onto the original VIC-II chip and tested that in the ZIF board, and it works fine as well. So we have a good VIC-II, a good CPU, theoretically all good RAM, good multiplexers. We haven't tested any of this logic, but assuming that it's good, our options are limited at this point. We need something. Address lines 8, 9, 12, 13, 14, and 15 were all acting wonky. So I went looking for other things. Now there's the 373 is on a lot of those lines. But before I did that, before I went to the trouble of desoldering that, I decided to check something else out. Now I don't know why I thought to do this, because this absolutely should not have been the problem. We replaced the PLA. This is a brand new PLA. This comes from a batch of new old stock PLS 100s that someone found and programmed as PLAs. And up until now, all of the PLAs that I got out of that batch have worked absolutely perfectly. But I thought, okay, it is on some of those address lines. It could be causing a problem, so we'll test it. So I tested it in the ZIF board. And I will show you doing that again. I couldn't see anything in the signaling that screamed to me that it was bad, except the addressing was going all screwy. But the signals it was giving looked relatively correct. So I really honestly don't know why I checked this. But turns out it was a good idea. Because when I pop the PLA out of the ZIF board and put the suspect one in, power it up, the ZIF board now gives me a black screen. And I have tried reseating this, still a black screen. Reseat it again, still a black screen. So this replacement PLA is actually bad. So I'm going to change my mark to an X, and this machine is now the proud owner of 2 bad PLAs. Now this is the original PLA from the ZIF board, so we'll make sure that we're still working. And we are. So I will grab another replacement PLA from my stock, put it in here, make sure it's working, and it is. So we have a working PLA. Grabbing the board back again, PLA, and again remember the VIC-II always points to the PLA, so it's this socket, and I'm not screwing that up again. And with the new PLA, what happens with dead test? And now I'm getting a flash. Okay. Looks as though the CPU is not working now. I'll have to test that in the ZIF board in a minute, but for now, let's put a replacement CPU in, and the original VIC-II with replaced pins back in. And we get the dead test. So possibly have a dead CPU. Now, you won't necessarily believe me when I say this, but the truth is, I tested this with the replacement PLA off camera when I was figuring all this out, and I found it to be working with the CPU that we have here, the one that shows bad. Now, this CPU was working last night. Today, not so much. We'll let this run through dead test. Okay, that's a successful dead test. Now, you see the timers are messed up, and that's obviously because there are no CIAs in this board. So that's to be expected. So now, one by one, I'm going to put the other chips back in to make sure, testing each time so that if one of them happens to be shorting out the address or data bus, we'll get that indication. So we'll start with the CIAs. I'm not going to do a full test. I'm just going to see if it comes up into dead test. That'll indicate there's no bus, address bus or data bus conflict. And we're good. U2. Still good. Basic ROM. Still good. As usual with the ROMs, you're not actually testing that there's data in them because they're bypassed by the dead test, but you can tell if there's a short or if there's a problem with the address or data bus caused by them. Kernel ROM. Good. Character ROM. Good. And SID. Dog hair. Good. All right. Now we'll switch to standard diagnostics, the enhanced version. And let's go for broke with the full harness. Okay, harness is in. We're in regular diagnostic mode, and let's give this a shot. Oof, that's not good. You know what? I think that's a CIA problem. I've seen that kind of corruption before, and U2 and the VIC-II do interact with each other. So I'm going to pull U2. I have a replacement here. See if this helps. Didn't have any bent pins, but let's see what happens with the different U2. And there it goes. So U2 appears to have a problem. We'll recheck that in the ZIF board in a minute. The timers are matching. Okay. I'm getting bad on the cassette port, and the CPU read bad. Let's reseat the cassette port and try that again. On a happy note, the SID sounds good. I have a couple things now I want to check with the ZIF board. I want to test the harness on the ZIF board, and I want to test that CIA. So the CIA in U2 did in fact test bad, and replacing it, obviously, as you saw, solved the problem with the video. So the next thing that I did was check the test harness to make sure that the failure on the cassette port wasn't a false failure. The test harness was in fact working fine, so it was time to figure out what was wrong with the cassette port. Now, I haven't had a lot of experience working with the cassette port, so I had to dig into the schematics and dig into the diagnostic program to find out exactly how it was testing the cassette port, what it was doing, and if I could use that information to narrow down my search for the problem. So I started by looking at the C64 diagnostic instruction and troubleshooting manual that I found online. This is obviously for a different version of the diagnostics, but I think for the cassette port, it should be accurate. And if I look on page 8, we see the cassette port test procedure. However, before we look at the test procedure, it's important that we know more about the Commodore dataset and the cassette port. Here's an example of dataset, also known in its varying incarnations as the C2N or the 1531. Like I said, it came in several different incarnations, all of which function basically the same, dating back to the Commodore PET 2001 and extending all the way through the Commodore 16, 116, plus 4, and even the Commodore 128. One thing you'll notice is that all of them bear only a single cable, the one connecting it to the computer. There is no separate power cord or external power supply. If you open one up, you won't find an internal power supply either. That's because the dataset receives all its power from the computer to which it's connected. Both the 5-volt DC rail used to power the logic board and the 6-volt DC rail used to power the drive motor are supplied by the computer via that single cable. Commodore just had to be different. In addition to the 5-volt DC ground and 6-volt DC cassette motor conductors, that single cable also carries the cassette write, cassette read, and cassette sense signals on 3 additional conductors. This makes for a total of 6 conductors required between the dataset and the computer. The cassette port on the various Commodore computers is a 12-pin card edge connector with 6 conductors on the top and 6 on the bottom. But as you can see, the signals on the top conductors are mirrored on the bottom. For purposes of this troubleshooting, I don't think it's necessary to go into how those signals work or what they do. It's interesting though, so if you've got some time to kill one day, it'd probably be worth your while to look into it. Again, Commodore just had to be different. Looking here at the schematic for the 250425 taken from Bo Zimmerman's excellent Zimmers.net website, you can see the cassette port and we can trace where they go. Plus 5 volts and ground just tie to the main plus 5 volts and ground rails on the motherboard, being supplied from the plus 5 volt line coming in from the external power supply. Cassette write, cassette sense, and cassette motor are connected to pins 24, 25, and 26 on the 6510 MPU. These pins represent bits 4, 5, and 6 of the 8-bit programmable I/O port that represents one of the differences between the 6510 and its baby brother, the 6502. Calling this I/O port programmable refers to the fact that each bit can be individually defined to be an input or an output at runtime. The final signal, cassette read, connects to pin 24 on the 6526 CIA at U1, which is the flag pin. Now that I had a better understanding of cassette operation, the next thing I needed to determine was whether the diagnostic result gave me any better indication where to look for the fault. So turning back to the diagnostic instruction and troubleshooting manual and the section covering the cassette port test, we find that the diagnostic runs two tests, one each on two pairs of signals. Based on the definition of these tests, it becomes obvious that the cassette port dongle in the test harness provides two loopbacks and apparently a little voltage correction. First, cassette read and cassette sense are tested by sending low pulses out on the cassette sense line and listening for those pulses to be returned on cassette read. Second, cassette motor and cassette write are tested by sending low pulses out on cassette motor and listening for them to return on cassette write. The first test involves the cassette port, the 6510 MPU, and the 6526 CIA at U1. The second involves only the cassette port and the 6510 MPU. Therefore, it seemed likely to me, since the diagnostics were reporting the cassette port and the 6510 as bad, that the failure was happening during the second test. I wanted to verify my deductions though, so I dug out a working 64 board, hooked it up with a diagnostic cartridge and test harness, and made sure it tested okay. Then, to see if we'd get a different diagnostic result if it were test 1 that failed, I cut the trace going to cassette read, pins 4D, on the cassette port and ran the diagnostics again. Sure enough, I did get a different result. The diagnostics showed the U1 6526 CIA as bad, along with the cassette port. So I bodged back across the trace I cut, and I put that board away. So now that I'd verified my deductions and confirmed that the second test was failing, I could focus my attention on the 6510, the cassette motor circuit, and the cassette write circuit. We've already tested the CPU with the harness and the ZIF board, so I felt fairly safe eliminating it from contention. Similarly, we've already tested the test harness dongle, which was fine. As you can see in the schematic, the cassette write circuit doesn't have much on it to fail. Just a 100 ohm resistor and a 470 picofarad capacitor. The resistor tested fine, and I didn't try testing the capacitor because to do so with any degree of confidence, I'd have had to pull it out of the board, and I decided to only do that if I couldn't find a problem anywhere else. That left me with the cassette motor circuit. It's unfortunately the most complex of all of them. Truthfully, a full understanding of the circuit isn't necessary to test the individual components for failure, but I dug into it anyway. Let me preface this by saying again that I am not great at analog electronics. I do much better with the digital stuff, and transistors always throw me for a loop, and there are two of those in here. So if I make any mistakes, which I'm sure I will with this explanation, please correct me in the comments below. I'd be very glad for the help. So, coming off the cassette motor line, we have a 1K resistor, which I believe limits the current being delivered to the base of Q4. Q4 then appears to be a switching transistor that turns on the rest of the circuit when power is applied to its base. When it's turned on, it allows the unregulated 9-volt DC, which comes from the power supply section of the board just after the bridge rectifier and the two smoothing caps, and is then current limited by this 470 ohm half-watt resistor to flow through this junction, where it gets clamped down to 6.8 volts by this Zener diode and then into the base of Q1. Q1 is an NPN power transistor in an emitter-follower configuration, which will drop the voltage slightly by approximately 0.7 volts due to the diode drop of the collector base junction, but amplify the current. Q4's HFE, or beta, according to its datasheet, is between 60 and 300. So the current at the emitter, I sub E, is between 60 and 300 times as large as the current at the base. This is necessary because that 6 volts DC, approximately, will be used by the dataset to drive the 6 volt DC motor. Got all that? Good. Now forget it because it's not important. All I really need to do is test each component individually. I did this with them all in circuit, which isn't ideal, but can sometimes work. Both resistors were good. Then I tested Q4 and Q1 by putting the meter in diode mode and measuring in forward bias between the base and collector and then base to emitter. Both junctions on both transistors showed a reasonable voltage drop. Testing in reverse bias gave me over limit, OL, as did testing in either bias between the emitter and collector. As far as I could tell with the transistors in circuit, they were both working normally. Finally, I tested the Zener diode, again in circuit. In forward bias, the meter showed a voltage drop of 0.004 to 0.006 volts. I was expecting to see something more along the lines of 0.6 to 0.7 volts. In reverse bias, I didn't get the expected over limit, but got a voltage drop instead. These readings were enough for me to suspect the little Zener being the problem, so I took it out of the board and retested it. Still no bueno. So I replaced it. I happened to have one on hand in my spares. Just for completeness, I'll tell you that the other important characteristic of a Zener diode, its breakdown voltage, can only be tested by building up a circuit and actually testing it in action, so to speak. In this case, that wasn't necessary because the easy-to-test characteristics were way out of spec. So that's where we're going to pick up. I've just replaced the little Zener, and let's see if that's done the trick. What do we get? That was our issue. Bad Zener diode. Okay, there's one thing left to test, and that's to make sure that the SID is fully functional. To do that, you know what we're going to do. Get the harness disconnected and put away. Get our Easy Flash cartridge. And our controller joystick. Power and so it looks like this machine's now working. I did realize that I forgot to go back and test the 5-volt rail again to see if it was still showing low. I did that off camera and found out that it was indeed still low. So I traced it around the board and came to the conclusion that it was the power switch. Sometimes those power switches do get dirty inside and don't conduct electricity quite the way they should, which I believe is the case with this one. So I'll have to clean it out at some point, but in the meantime, I just went ahead and put a brand new switch in. After replacing the switch, I'm now getting a good, healthy 4.85 to 4.87 volts on the 5-volt rail. The final tally for this machine ended up being quite extensive. We started with a bad fuse. the PLA was bad. Somewhere along the way, the replacement PLA, which I had tested and verified was good at the time I installed it, got damaged and had to be replaced again. We found some more of those non-socket sockets under the RAM. There were 4 empty RAM chips on the board, which we replaced out of an abundance of caution. We also had 2 MOS-branded multiplexers, which we replaced, although they did both test good in the TL866. We replaced 2 broken pins on the VIC-II, after which it tested good. We replaced the marginal 6510 CPU. A 7406 logic chip was bad. The 6.8 volt Zener diode in the cassette motor circuit needed to be replaced. And last but not least, the power switch was faulty. I don't know about you, but I'm exhausted. So it's time for me to call it a day. I hope you enjoyed the video, or at least that you learned something from it. I know I certainly did. And with that, all that's left is for me to thank you for watching, wish you health and safety, and tell you that I'm looking forward to seeing you in the next one. Bye.